Imagine handing a complex, like extreme level Sudoku puzzle to a massive frontier AI model.
Oh, yeah.
We're talking Claude 3.7, DeepSeek R1671B, or O3 Mini. You give them the prompt and they fail completely, like 0% accuracy across the board.
Right. Completely hallucinating the answers.
Yeah, exactly. Now imagine taking a tiny, heavily optimized mob, I mean, less than 1% of their size, and watching it breeze through that exact same puzzle with over 91% accuracy.
It really sounds impossible, right? Given everything we assume about scaling laws. But that is exactly what we are looking at today.
We're jumping straight into a paper that makes this possible. It's called Solve the Loop: Attractor Models for Language and Reasoning by Jacob Fine-Ashley and Priya Rashidinejad from USC, and it was published in May 2026.
Yeah.
And for all of you AI researchers and ML engineers tuning in, here is the rapid-fire summary. So standard transformers are limited by fixed feed-forward compute. Looped architectures, like Parse, they try to fix this, but they suffer from highly unstable training and, well, massive memory overhead from unrolling the graph.
Right, which is a nightmare.
A total nightmare. But the solution here, they call them attractor models. This architecture uses a backbone transformer to propose an initial guess and a separate weight-tied attractor module that continuously refines it until it hits a mathematical equilibrium.
And, the performance metrics are what make this the actual structural breakthrough. I mean,
Yes.
O of 1 constant training memory, up to 31% fewer FLOPs, a 770 million parameter model beating a 1.3 billion parameter standard transformer that was trained on twice the tokens.
Wow.
Yeah, and as you mentioned, that staggering 91% accuracy on hard reasoning where the literal giants of the industry fail.
Plus, and this is my favorite part, it exhibits this wild phenomenon called equilibrium internalization, where the model essentially learns to skip its own refinement loop at test time.
Exactly. It's fascinating.
So welcome to this deep dive on AI paper podcasts. Our mission today is to unpack exactly how these attractor models decouple training depth, inference depth, and memory, and why abandoning the idea of a fixed loop count might, completely change how we build reasoning models.
I'm really excited for this one. It really is an elegant solution to a problem the industry has been wrestling with for, well, a long time now.
Yeah, let's set the stage a bit for the listener.
Sure. So if we connect this to the bigger picture, we all know that single-pass token-by-token generation is a massive bottleneck. The traditional way around this is chain of thought, right? Forcing the model to think by dumping its intermediate steps out into the discrete text token channel.
Right, the model basically has to talk to itself out loud just to figure out the answer.
Exactly. It's writing everything down on the whiteboard. But researchers have increasingly realized that writing everything down token by token is incredibly inefficient.
It's slow, super slow. So the field started looking at latent or implicit thinking. This means looping computations internally, inside the hidden layers, before ever outputting a single token.
Like keeping the thoughts in its head.
Yes. You see this in architectures like universal transformers or Parquet or Arrow.
Okay, let's unpack this. We want the model to think in the latent space because it's richer and faster. But doing that introduces a massive technical headache.
Oh, a huge one. Because to train these looped models, you typically rely on an algorithm called backpropagation through time, or essentially backpropagation through depth.
Okay.
This means for every single internal loop you run during the forward pass, you have to unroll that entire computation graph to calculate the gradients backward.
So wait, if I loop my internal reasoning 10 times, my memory footprint basically multiplies by 10.
Precisely. Your memory requirements scale linearly because you have to store the intermediate activations for every single one of those 10 steps.
Yeah, it becomes prohibitively expensive, leading to out-of-memory errors very, very quickly. But memory isn't even the only issue here. You also run into a severe test-train mismatch.
How so?
Well, if you train a loop language model to refine its thought process exactly 5 times, right, and then at inference time you give it a harder problem and ask it to loop 8 times, the performance doesn't actually improve. It degrades.
Wait, really? Why would giving it more time to think make it perform worse?
Because the network was mathematically optimized for the dynamics of exactly 5 steps. The intermediate representations are trained to expect a specific sequence.
Okay, I think I see the issue. It's not like giving someone more time to ponder. It's more like a rigid mechanical assembly line.
Exactly.
Like if a factory is perfectly calibrated for a 5-station conveyor belt and you suddenly drop a 6th station in the middle of the floor, the timing mechanism just shatters. The parts don't line up anymore.
That's a great way to put it. The sequence is completely rigid. So the authors of this paper ask, how do we abandon this rigid fixed loop count entirely?
Right. And that led them to the attractor model architecture, which uses a two-stage process. You have a backbone module and an attractor module.
Let's break those down. The backbone is just a standard causal transformer, right?
Yes, but its role is highly specific. It takes the input tokens and outputs what the authors call an initial guess embedding. It's denoted as util_0.
Okay, util_0.
And what's fascinating here is that this initial guess is a highly informed proposal. It's taking a really solid first swing at the final representation based on the context.
As opposed to what? Like, what did older models do?
Well, in older continuous depth approaches, things like deep equilibrium models or DEQs, they would often initialize the recurrent state with a blank zero vector or just random Gaussian noise.
So the model was essentially waking up with total amnesia and trying to build a complex thought from absolute scratch every single time. Exactly. And starting from scratch like that led to massive instability during training. The network had no anchor. But here, the backbone provides a very strong starting point. Then we take that util_0 proposal and pass it to the attractor module.
And this is where the magic happens, right? Because the attractor is a smaller weight-tied transformer network. But it doesn't just run 5 times or 10 times. It uses a root-finding algorithm.
Specifically, Anderson acceleration. In the forward pass, it treats the refinement process as a search for a mathematical equilibrium, a fixed point.
Okay, stop right there, because if we lose the ML engineers on the math, we lose the whole point. What is Anderson acceleration actually doing mechanically?
Fair point. Fair point. Think of a standard loop as just blindly taking a step down a slope to find the bottom of a valley. You take a step, reevaluate, take another step.
Standard gradient descent stuff.
Right. Anderson acceleration is smarter. It keeps a memory bank of the last few steps you took. It looks at the history of those steps, calculates the trajectory of where they're pointing, and essentially skips ahead.
Oh, wow.
Yeah, it aggressively jumps closer to the bottom of the valley. It accelerates the convergence to the equilibrium.
Okay, so it's continuously running this accelerated loop, comparing the output of the current step to the previous step. How does it know when to actually stop?
It looks at the residual difference. It stops when the change between step t and step t-1 drops below a specific microscopic tolerance level. They call it epsilon.
Right.
Or, it stops if it hits the hard maximum step limit as a failsafe.
Right.
But the primary goal is to find the state where further computation literally does not change the answer.
I love this. It's the difference between pouring water into a glass for exactly 5 seconds, just blindly hoping it doesn't spill over, versus pouring water with a smart sensor that perfectly detects when the glass is full, regardless of how long the tap was running.
Exactly. It's dynamic depth based on the actual complexity of the input.
But I have to push back here. If the attractor module is just looping over and over again, feeding its own output back into itself to find this equilibrium, doesn't it eventually drift?
What do you mean?
Like a copy of a copy of a copy. Doesn't it sort of forget the original prompt and just collapse into some generic, meaningless vector?
This raises a very important question, and it is a very real danger with recurrent networks. If left completely untethered, the model will often just collapse into a state that ignores the input entirely.
Right, just finds the easiest mathematical resting place.
Exactly. But the authors addressed it with a brilliant yet simple mechanism called persistent additive injection.
Additive injection, so they are adding something back in.
Yes. In the paper's ablation studies, they show what happens if you just let the attractor loop on its own. The convergence rate is a measly 12.4%. The model completely loses the plot.
Wow, 12% is terrible.
It's awful. But if you take the original backbone proposal, that highly informed v_0 guess, and you add it back into the representation at every single refinement step, the convergence rate skyrockets to 99.7%.
Oh, wow. That's a night and day difference. So formulaically, you are processing the current step plus the initial guess. By constantly injecting that initial context back into the loop, you anchor the reasoning. The model is allowed to explore and refine deeply, but it's physically tethered to the reality of the original prompt.
It forces the equilibrium to remain highly relevant to the specific input tokens. It cannot drift into a generic fixed point because the prompt is constantly pulling it back.
Okay, this all sounds conceptually beautiful, but I want to get to the thing that is going to make every engineer listening actually care.
The efficiency.
Yes. Let's talk about out-of-memory errors. OMs are the absolute bane of training models. Earlier, you said that unrolling loops causes memory to scale linearly because PyTorch or JX has to build a massive computation graph.
Right.
But the summary said this attractor model operates in O of 1 constant memory.
That is correct.
Wait, how is that mathematically possible? If the Anderson solver loops 50 times to find the equilibrium, PyTorch still has to backpropagate through 50 steps, right? How does that save memory?
This is where we get into the magic of the implicit function theorem, or the IFT. Because we define the forward pass as explicitly solving for a root, an equilibrium state where the output equals the input. The backward pass does not need to unroll the graph. The IFT tells us that the gradient at the fixed point depends only on the state at that fixed point, not the trajectory the solver took to get there.
Hold on, so PyTorch just throws away the 50 steps.
Essentially, yes.
Yeah.
Imagine you drop a ball into a complex, bumpy valley, and it rolls around for 10 minutes before finally settling at the very bottom.
Okay, I'm picturing it.
If you want to know how the ball's final resting place will change, if you slightly shift the tectonic plates beneath the valley, which is what backpropagation does, it shifts the parameters. You don't need to know the 10-minute path the ball took.
You just need the final spot.
Right. You only need to calculate the exact slope of the ground at the specific spot where the ball is resting. The destination tells you everything you need to know to calculate the gradient.
That is incredible. You only pay the memory toll for the destination, not the journey. So your memory footprint is totally flat, whether it took 5 loops or 50.
Exactly. But there is a catch.
Of course there is.
Calculating that exact implicit gradient at the destination requires solving another complex linear system. Specifically, it involves something called the inverse Jacobian matrix.
And whenever I hear inverse Jacobian, I assume the computation is about to get brutally expensive.
You would be right. It's a massive grid of partial derivatives. So while we solved the memory problem, we seemingly created a massive math compute problem. To fix this, the authors used a specific trick, the one-step gradient approximation.
How does that work?
Instead of calculating the full, mathematically perfect inverse Jacobian, they approximate it. They essentially make an assumption. If the attractor's pull toward the equilibrium is strong enough, the final refinement step points almost perfectly toward the root anyway.
Right.
So they reduce the entire backward pass through the attractor module to a single vector Jacobian product based on just that final step.
So they just use the slope of the very last step to estimate the whole thing. Does the performance actually hold up with an approximation like that?
It holds up beautifully. The ablation study in the paper shows the one-step approximation maintains nearly all the quality of full backward gradients, but it enables incredibly fast and efficient training.
That's wild.
Yeah, and if you look at the charts for peak training memory, the attractor model is literally a flat horizontal line, O of 1 constant memory. Meanwhile, the baseline loops model, parse, shows memory spiking exponentially until it hits a hard O error as the loop count increases.
And I imagine this saves on actual compute operations, too.
Significantly. Because the attractor solver often finds equilibrium well before hitting the maximum step limit, the total training FLOPs are reduced by 25 to 31% compared to parse. It's faster, and it is infinitely more memory efficient.
Okay, here's where it gets really interesting. This is the part of the paper I had to read twice. They call it equilibrium internalization.
Oh, this is the best part.
Right. So we've built this elaborate, beautiful solver with Anderson acceleration to iteratively refine the embeddings, searching for this perfect fixed point. But what happens when the backbone module, the part making the initial guess, gets really, really good at its job?
What happens is the backbone effectively learns to predict the future.
Mm-hmm.
Because the entire network is trained end-to-end, the attractor module acts as an automatic curriculum for the backbone. Think of the attractor as a moving teacher.
Okay, I'm following.
Early in training, the backbone makes a rough, sloppy guess. The attractor has to work really hard, running many loops to pull that guess toward the true equilibrium. But over time, the gradient signal to the backbone exactly where that final fixed point is.
Oh, I see.
Yet by the end of training, the backbone's initial guess, y=0, lands almost exactly on the final equilibrium state right out of the gate.
So if we use a human analogy, it's like developing muscle memory for complex math. When you first learn long division, you have to write out all 15 steps on a piece of scratch paper. That's the attractor looping.
Perfect analogy.
But after doing it 1,000 times, you internalize the pattern. You look at 144 divided by 12, and your brain just instantly outputs 12. You skip the scratch paper entirely.
Exactly. The backbone is developing representational muscle memory. And the inference graphs for this are jaw-dropping. For the looped baseline, parse, The validation perplexity only gets to its peak performance if you force it to run exactly 8 iterations at test time. If you want fewer, it falls apart.
Right.
But for the attractor model, the performance is completely maxed out at just 1 iteration.
Wait, they tested it at 0 iterations too, right?
Yes, what they call t equals 0, meaning at inference time, you literally just take the backbone's very first guess, you turn off the attractor solver entirely, and you just decode that initial embedding.
It works.
The 770 million parameter model still performs beautifully at t equals 0. In fact, it actually performs better than the baseline models that require heavy looping.
So you train the model using this heavy, recursive, deep thinking process, but at deployment, you get the low latency and speed of a standard single-pass feed-forward model. It has fully internalized the recursive reasoning.
Exactly. You get the representational power of a deep, recurrent network, but the deployment profile of a shallow one.
Wow. So what does this all mean when we actually put it to the test? We've got the theory, we've got the math. Let's look at the empirical smackdown. The paper evaluates this across 2 totally different regimes: large-scale language modeling and tiny model hard reasoning.
Let's start with the language modeling.
Let's do it.
The authors used a standard NanoChat recipe, training on the FindWeb eDo dataset. They compared models at 140 million, 370 million, and 770 million parameters.
Very standard sizes for this kind of test.
Yeah, and they matched the parameter counts, data budgets, and optimizers perfectly against standard transformers and the Parse looped model. Across the board, the attractor model is a Pareto improvement. It achieves lower validation perplexity, better downstream accuracy, and requires less training compute.
And the scaling is where it really shows its teeth. I'm looking at the chart here. The 770 million parameter attractor model achieved better out-of-distribution perplexity on the Lambda data set and better accuracy on the core benchmark than a 1.3 billion parameter standard transformer.
You think about that.
A model almost half the size, beating a baseline that was trained on twice as many tokens.
It proves that giving a model the architectural capacity to refine its latent thoughts is mathematically far more efficient than just scaling up feed-forward parameter counts and blindly throwing more data at it.
Okay, but we have to talk about the reasoning benchmarks, because this is the data from the intro that is going to make every technical listener sit straight up. They tested these architectures on tiny model reasoning setups, Sudoku-Extreme, and Maze Hard.
This is where we see a complete bloodbath for traditional architectures.
Bloodbath.
I mean, these tasks require strict, algorithmic, multi-step deduction. Standard feed-forward transformers, even massive ones, struggle with this if the exact step-by-step logic isn't heavily represented in their training distribution. The authors tested the current frontier models on these specific, rigid setups. DeepSeek R1, 6721B, 0.0% accuracy.
Insane.
Claude 3.78K, 0.0%. OpenAI's O3 Mini High, 0.0%.
It's almost comical. Hundreds of billions of parameters, and they just fail.
And a standard 27 million parameter transformer also gets 0.0%.
Yeah.
They simply cannot solve the algorithmic constraints purely through token prediction.
So standard scaling fails completely here. What about the specialized recurrent models, the ones built specifically for this kind of logic?
There are specialized tiny recursive networks, or TRMs. At 7 million parameters, a TRM does decently well, scoring around 74 to 85%.
Okay, so that's something.
But TRMs suffer from a known less is more paradox.
Yeah.
When the authors tried to scale the TRM up to 27 million parameters to get better performance, the architecture completely collapsed. It dropped to 0% accuracy.
Wow.
Yeah, the recurrence became totally unstable at that size.
The loops basically tear themselves apart, and then we drop the attractor model into the ring.
With just 27 million parameters, trained on only about 1,000 examples. The attractor model achieves 91.4% accuracy on Sudoku-Extreme and 93.1% on Maze Hard.
That is absurd. Why does it survive scaling when the TRM collapses?
Because it is solving for a mathematically grounded fixed point, rather than blindly unrolling a sequence of steps. The Anderson acceleration and the additive injection keep the representation stable.
So it's robust.
Highly robust. It doesn't collapse when you scale it from 7 million to 27 million. It scales up cleanly and powerfully. It maintains its anchor where other recurrent architectures just drift into noise.
Okay, let's bring this all together. What is the core value here for you, the listener? Attractor models have successfully decoupled inference depth, training depth, and training memory.
Yeah.
By formalizing latent reasoning not as a rigid number of steps, but as an output space equilibrium, we finally get the stability of standard transformers combined with the raw algorithmic power of recurrent networks.
And we get all of that while completely dodging the memory tax of backpropagation through time by relying on the implicit function theorem.
It's a massive step forward for both efficiency and reasoning capability. We're moving away from forcing models to think out loud via text tokens and giving them a stable, mathematically sound way to think deeply in the latent space.
It really is a paradigm shift.
So I want to leave you with a final provocative thought to mull over. We've talked about how this model fully internalizes its own recursive reasoning. It literally teaches its single-pass backbone to instantly guess the end result of a complex looping thought process.
Right.
So what does that mean for the future of System 2 thinking and AI? Could we soon see a paradigm where we train massive, incredibly slow-thinking recursive models in the lab, letting them grind through complex logic for hours to find perfect equilibria, only to have them naturally self-distill that deep logic into lightning-fast System 1 models that can be deployed instantly on your phone?
That's the billion-dollar question.
The architecture to do exactly that might have just arrived. Thank you for joining this deep dive on AI paper podcasts. If you want to dig into the math, look at the ablation studies on additive injection, or try running the Anderson solver yourself, definitely check out the code base and the website linked in the paper. Until next time.